Okay. Hello everyone. Welcome to this session. My name is Batuhan. I'm a high school student from Turkey, and in this session I'm going to talk about LLVM and Python. This talk is specific to Python and the approaches taken by Python's JIT compilers using LLVM, but there are some good points that can be used in compiling dynamic languages to LLVM IR. We are going to start with CPython's workflow and pipeline. You may see this are irrelevant, but most of the applications use these workflows, pipes to generate IR, LLVM IR, and JIT compile. Then we are going to see dynamic nature of CPython, like why you shouldn't trust user code, and why we can easily convert Python to LLVM or other representations. Then we are going to see some projects that are not currently under development and dead because of some reasons. The first one is Unladen Swallow. It's a Google-sponsored fork of CPython, which tried to bring LLVM into Python's core. But then Google lost its interest, Google's clients lost its interest, so it's that. Then there's Py2LLVM and PyLLVM. Py2LLVM was an old project by an indie developer, and it is retrieved as PyLLVM, and the both are dead right now. It's a JIT compiler for Python 2. And Piston is a relatively new project. It is sponsored by Dropbox, but then Dropbox switched performance critical code to other languages such as Go, and it is also dead. There are some current projects like Numba. Numba is a JIT compiler for NumPy, Python, mathematical oriented code, which uses LLVM Lite at the backend. LLVM Lite is a Python binding to LLVM, which offers a great API, and it offers a way to access JIT execution engine of LLVM. And in the future part, we are going to see how we can implement and develop a JIT compiler for Python in two ways. One is converting Python's AST into the LLVM IR, and one is converting Python's bytecode to LLVM IR. We are going to start with CPython's workflow. CPython takes your source and generates tokens from it. Tokens are individual parts, and they have no relations. Then the CPython's parser takes the tokens and constructs a concrete syntax tree, which has relationships, but it is hard to work on. And then it strips all of the irrelevant information from that concrete syntax tree and constructs an AST. And then through the AST, it constructs a control flow graph-like structure. There are no real control flow graphs in CPython, but there's some structure that like control flow graph, and it generates bytecode from the AST and that structure. And then it executes that bytecode in Python's virtual machine. The AST and bytecode is suitable for code generation, but the other parts aren't. And let's see them in details. The tokenization starts with reading your Python file, like it should be a .py file or the standard input, that doesn't matter. Python reads the file, decodes its contents in the encoding you have specified, or the UTF-8, and it tokenizes it with certain patterns, like that patterns depends on the context. It knows how to split A.B. A has an individual meaning by its own, B has an individual meaning by its own, but it doesn't split 1.1 because 1.1 is a float. But you can use tokens to generate machine code because there are no relationships, no blocks, no nothing. It's a pretty raw format. Like this is a... okay. Can I highlight this? Yeah. This is some tokens, like one is number, operator is plus. I know you can't see it because of highlight. Yeah, the number, this is 1 plus 1, but you can't generate code from this because there are no relationships. Then there's a parser. Parser is a program that takes that generated tokens and uses rules to construct a tree-like structure, concrete syntax tree. It's pretty complex because there's irrelevant information such as white space or parentheses. There are relationships, but the blocks aren't suitable for direct code generation. And Python's parser interface is deprecated and will be removed. So Python advocates the work on in AST level. AST is the abstract version of that concrete syntax tree. There are nodes that are defined in ASTL format, Zephyr's ASTL format, which are easy to work on. Like when you parse a function, it says this is the return, this is the function's name, this is the annotations of the function's code, etc., etc. Python says you can manipulate AST or generate your code from AST. I give you some interfaces, some helper functions, but don't use the parser because it's so raw. And it keeps only relevant information for generating code. Like it doesn't keep any white space or comments. It keeps line no information for syntax errors, for highlighting like where this syntax error happened. This is an example of Python's node visitor interface. You can, whenever Python sees a constant node, it will call the visit constant handler. Whenever it sees a name node, it will call the name handler. So you can generate intermediate representation here. Then after that AST step, Python will construct code objects that contains bytecode and some information. This code object is going to execute under CPython's virtual machine, which is a stack-based virtual machine that works like you push something, you pop something with the instructions. The instructions are formatted like there's an opcode and oparg, operation argument. And there are some extra sequences, like if you use a load const opcode, you specify argument as an index of co-const data structure, so it will make the Python faster. Unfortunately, there are no direct interfaces to assemble bytecode in Python itself. There are interfaces to assemble AST in Python, but there are interfaces for disassembling bytecode objects, which we can use in JIT compiling the functions body. This is an example function that takes x as an input and compares if x is greater than 4, returns power of 2, etc., etc. And when we disassemble this, we see instructions like this. The first one is a load first. It loads the local variable from the argument spec, and they are formatted like this. This is jump target thing. Python stack-based virtual machine operates like this. It checks if x is greater than 4. If not, it pops directly here. If it is true, it runs this place. So this is a jump target from that return power of 3 line. Yeah. This was the workflow of CPython. Let's see why we can't directly trust the user code, because we won't give the types of the arguments or any kind of name. They are all dynamic, and it will make our job harder. User can even change built-ins, like user can change lamp function, or they can even put handlers inside of class definitions. Like when you define a class, Python loads something called build class, which is a helper function. And when you change build class from the built-ins module, whenever someone defines a class in Python, your function gets called. And this makes things even more harder. And compared to other languages, in Python, everything is mutable unless you say otherwise. Yeah. Let's see some attempts from the past that tried to integrate LLVM with the Python itself. Unladen Swallow, it's a Google-sponsored fork of CPython that tried to make a JIT compiler for CPython itself. Its name comes from Monty Python show. It tries to make Python faster. It starts for a fork of CPython, and they plan to eventually merge this into the Python's core, but then there are some side effects which prevent this. It was sponsored by Google, and then Google lost its interest because this was a fork and deployment was hard. Google hasn't any performance critical code in Python, and Google's clients don't want to allocate money and time for this. Its features, it made Python 2.5 times faster on single-thread Python code. It's single-thread. They didn't solve the global interpreter lock problem. In Python, if you have a CPU-bound code, it can run. It runs one thread at a one time. It doesn't matter if you have 4 threads. It runs one thread because of some reference counting issues. And Unladen Swallow didn't solve it, but it's make Python faster 2.5 times in single-thread code. Their aim was 5 times, but there are some problems about reaching that aim. They didn't break any Python code because they were already based on CPython itself. So every C extension run as usual. They analyzed Python code before running it, so they know if you change the lamp function or not. So that they make some assumptions performed on this and some data collected at runtime, like what X function gets. If X function gets always integers, they said, okay, generate intermediate representation based on that fact. But if it gets a string, there's a guard which prevented these assumptions false. It converts bytecode. It operates in the bytecode level instead of ASD, which is their choice. There is a hot threshold in Unladen Swallow. So there's a cost of making a function compared to LLVM. So if a function called so many times and they know so many about it, they compile it to LLVM. And before that compilation, they collect data about that function. Help of the data. They know They know if there is a if branch never executed, they just cut out it. Or if they know all arguments are integer, they optimize for that. But ensuring that everything works as same, even the arguments changed, they put guards which has costs if mispredictions happen. And they worked with linking LLVM into the Python binary. There are some cons, bad sides of this. One is memory usage. The memory usage increased up to 8 times. It's not always 8 times, but the most part of it 8 times. This is one of the causes of LLVM and other libraries. They increase memory usage. And if you keep different versions of same code in the memory, it will increase by default. So they keep the native code, they keep the bytecode, they keep the ASD, so memory is increased. And there are some optimizer structures. They tried to optimize Python bytecode before sending to LLVM, so they create some structures which keeps Python's internal knowledge, but they have their cost. There are some cons about startup time, static linking again. And when you want to compile a Python function to LLVM, you need to initialize LLVM, and C++ initialize take some time. And there are some over the top C runtime routines. Binary size increased as usual because you linked the LLVM. Why don't they reach the 2.5 times? They reached 2.5 times, but not 5 times. Because when they was working, this project was from 2009. LLVM isn't that good at just-in-time compilation, and they had some issues with that. And LLVM's JIT code doesn't work well with GDB. If you are developing a C extension in Python, you probably want to debug it with GDB on seg files and use O profile. and LLVM's JIT code didn't work well, so they allocate some time to fix these, but they lost some gain in performance. This project lasted 1 year, and then Google lost its interest. If the project continues, in my opinion, they can reach the 5 times goal easily on some codes. Some LLVM points about this. They initially selected LLVM because they don't want to generate assembly code on every machine target. LLVM was easy. The optimizations and code generation was great, but in 2009, it isn't directly suitable for JITing, and cost of operations compiling was so heavy. Without collecting runtime data, it is hard to optimize. They was collecting after learning this, so they spent some time to do this without collecting runtime data. The next project is PyLLVM, which is a compiler for subset of Python that specializes in machine learning, algorithms, and computations. In Python, mathematical code gets executed slowly because of there's an overhead of dynamic things. If you compile this to LLVM, you get so much gain, and they try to do this. Their features are they are as fast as C code in some cases that compiles with Clang. They only work for a subset of Python. If your function doesn't fit that subset, they directly return your Python function. If it fits, they return a wrapper around the JIT code. They don't collect runtime data, but they do static type inference and symbol table generation. Python has a symbol table which you can use that comes with standard library, but it doesn't give you anything about types. So you need to create your own symbol table which records types and infers the types, which could be cool. They use something called LLVM Py, which is a library, a wrapper library around LLVM's API, C++ API. They use Python AST module instead of bytecode, which is more suitable, in my opinions. They try to convert the function body, and if they see something that can be converted, they raise an error, and if they catch that error, they return normal function. If they don't see that error, they just return the JIT function, and they infer the types. Let's see, Piston. Piston is a JIT compiler and a runtime for Python 2. Its runtime mostly based on CPythons, so they have some gain on that. They use something called tracing JIT, and they specialize on web applications, especially Dropbox itself. They managed to run Django's full test suite, as far as I remember. Their features as they are 95% faster than CPython in the latest release in 2017. They have C API support because of the CPython runtime, and in a big code base, you can run Piston with little changes over the general code base. They have more than 3 executors. LLVM is the highest level, and there's BJIT, and there's AST interpreter. So if your function gets called less, they interpret the function's AST. If it is called more than 25 times, they JIT with BJIT, and if it's called more than 1,000 times, they JIT it with LLVM. They have AST-like control flow graphs, and AST interpreter, 2 JITs, tracing, and they use something called inline caching and rewriting of functions body, and CPython-based runtime. So there are some projects from current dates. Numba. Numba is up-to-date project that uses LLVM to JIT. It's a JIT compiler. It's specialized in NumPy and Python functions. It knows how to bootstrap these to a assembly level and gets best performance. It's a subset, and it works only with type inference if it knows what types it gets, it directly JITs. If it doesn't know, it records runtime data. It's used with simple Python decorator. You just add something at top of the function called the JIT, and Numba automatically handles everything else. It supports NVIDIA, CUDA, and AMD ROG experimentally. It's almost as fast as C in some cases, which is pretty good. It works like this. It takes Python source. It uses bytecode to generate IR, and then it converts that bytecode to their own specialized intermediate representation. They made some assumptions based on type inference, and they generate LLVM IR and JITs afterwards. There is some different modes in LLVM and Numba. One is no Python mode. No Python mode means this object never gets Python objects. It always gets integers and other atomic types. So if you use it, you get more performance. Generates LLVM IR, and it optimizes it. LLVM Lite has an interface to LLVM, and you can optimize the bytecode. It binds the future. It finds functions. In the future, we are going to see how we can write our LLVM compiler. This is our target function. It takes A and B, and it uses Python's annotation feature, which we don't handle with type inference. You need to specify the types. We are going to use AST, LLVM Lite, the same library that Numba uses, and the annotations. This is the function. We will have a compiler. If we can convert the functions body, we will convert. If we can't, we will return the normal function. So it will work in a subset of Python. This is a basic compiler. It will try to get function source code. If it can't, it will return normal function. And if it can, it will parse the source code into the AST, and it will try to traverse that AST using node visitor class, Python's AST returned. If any error happens during that traversing, it will return normal function. So if something doesn't fit our subset, we will raise the compiler, and if this part catches that error, it will return the function. This is the AST of that function. It starts with a function definition. There is an argument part, there is a body part, decorator part, and return annotation. The module is the highest level of any AST, and we are going to generate an LLVM module from the Python's AST and set it to self mode. And generic visit is a function that traverses the body of given node. So we will give the body module, and it will traverse every node that lives under the module. This is the function, if you want to recall. The functions, first of all, we will remove the decorator that is used to JIT our code, so it won't be infinite loop. Then we are going to generate an argument spec from that. There's a cast LLVM function, which is just checks the annotation and converts an LLVM IR. And then we are going to get the return type. So we can convert an LLVM function type from that. It takes return type and the values of arguments. Then we are going to use that function type to generate an LLVM function, which will live under the module we have created. It will take the function type, and it will have the name of the node. Then we are going to append a basic block, which we can use that afterwards to get a builder in that basic block. So we are going to traverse the node's body one by one and use that builder to build our expressions. The first expression is constants. LLVM types doesn't directly fit to Python ones, so we need to convert it. Python's integers doesn't have a specific bit length, so we are going to use 32 for default, and we are going to use float for our float type, not double. This is the cast LLVM function. If the given type is integer, we are going to return LLVM's int type. If the float, we are going to return float type. And if the type is something we don't know, we will raise a compiler. This is the part that constructs intermediate representation, LLVM's constant, with the type of the IR and the value of the nodes. There's an argument access part. We will visit the name nodes, and if we can fetch the argument from the given function's type spec, we will fetch it and return the value. If we can't, we will raise a compiler because it's something global or we don't know. There is binary operations. We will try to get the operator from the builder object. If we can, we will raise a compiler because some operator we don't know. And then we will return the left side and right side under that operator. The return operation is pretty simple. We will just call read method of builder and return the given value, which is going to be binary operation. So we wrote a basic compiler with a compile class method, a compiler error if it doesn't fit the subset, and visitors for module function return binary operation name and constant. The funny part is creating an execution engine. We will create a default triple target that's configured LLVM and create a target machine. In the creating target machine, you can specify the optimization level or anything you want. Then we will create the execution engine, which takes a bootstrapping assembly. We don't have anything to bootstrap, and target machine, and we will return the machine engine. This is the jitting part. We will create the engine with this method, and then parse our module and verify it if it's a valid intermediate representation or not. Then we will add that module to our engine, we'll finalize and run the static constructors, and then we will get the function as a C-types function pointer. So at the end, we will fetch that function's pointer and cast it to C-types, C-func type. Python offers a way to access C functions with C-types. So there's a C-types, C-func type, which takes a type set, and the type spec is given here, and we will cast the function pointer to there. We did this with ASD, so can we do this same thing with bytecode? Yes, we will have something like this to decorate our function, and we will have that same part. We will keep a stack of the functions bytecode because Python's virtual machine is bytecode stack based. So we will visit the opcodes by one. If the opcode is something we know, we will add it to the stack. If we don't know, we will break the for loop and return the normal function. Loading names is simple. If we see a load fast bytecode, we will return the given argument to stack. If we see a load const, we will cast it to LLVM and append to stack. If we see a binary operation, we will pop two things from the stack and create an operation from it. And if we see a return value, we will return. This is the whole code to construct that IR. Yeah, this is it. Thank you for listening. Is there any questions? No? Okay. Okay.
So, you've been presenting several projects that fail to some extent to compile Python code into native code. And
Yes.
Can you make explicit what makes your proposition different? What are the things that are different in your approach than the one that were in Python?
Okay, you are asking what are things different in my JIT compilers other than the projects I presented. Okay, I need to go to the outline to list other other projects. Okay, this will. Okay, there was 4 projects. Unladen Swallow was using bytecode. the bytecode I am using in the second approach. So Unladen Swallow's approach and my approach is almost same. PyLLVM uses AST, and in my first approach I used AST to use that same approach. Piston and Numba also uses bytecode, so mine isn't different than others, but I try to simplify the process of their in my examples in both ways.
I have several questions.
Okay.
So the typing issue is a real issue for Python, and it seems to me that in your approach, you're delegating that to the user
Yeah.
to the type annotation. So that's actually a very big difference compared to the other approach. You're not taking care of type inference, which makes things much easier. But when you annotate a variable with int, it means Python int, which is actually big ints.
Yeah.
And you're casting them to 32 bits integer, which is a totally different word.
Yeah, I mentioned that LLVM types doesn't directly fit the Python type, so for the sake of easily, I casted it to 32-bit integer. But in a real world application, it would be nonsense to cast 32-bit int.
Yeah, or you could, for instance, using C types can exhibit 32 bits integers.
Yeah.
So you can ask the user to specify that it's okay to have hardware integers instead of.
Well, Python's typing doesn't allow to specify integers. There's literals, but there are nothing to specify the length of bit length of the integer in the type annotations, so it would be hard to user to define that.
How much of a speed up is your compiler getting?
Yeah?
How much of a speed up is your compiler?
My compilers get around to 20% speed because I don't do any optimizations, any extra thing. I just convert the direct Python to LLVM IR, and it gets 20% speed up.
What stops you from doing optimization? Why are you not running the optimizer?
Because for the sake of presentation, I want to keep everything simple. Okay.
As you're using type annotations, you don't need a JIT at all. You could do that statically. You just take the function and perform your static compilation, and then bundle the binary into your Python bytecode, and that's okay. So why would you use a JIT in your situation where you only use static information?
You are asking why I'm using JIT when there is already defined type annotations. I can just convert to functions by the ahead of time compilation. Because in the approach taken by like Unladen Swallow, they record runtime data. I want to keep that in my slides, but it doesn't fit. So I have a project called Swinging Ahead, which takes the exact thing like Unladen Swallow and it records runtime data. So you are right. In this way, it would make sense to not running JIT, but if you are going to record the runtime data or do other things, you need to use JIT.
Any more questions? When are you using the bytecode one versus the AST based?
To me, AST is much more simpler to work on. Because you don't need the extra bootstrapping code. Python offers an interface to access it. But I want to show how Unladen Swallow and Piston worked. So I an example to bytecode.
You see the AST one as the future. You see using the AST based one as the future.
Yeah.
One of the shortcomings presented by the Python author was that most of the Python code is actually just glue calling native functions. That's true for the standard library, but that's also true for third-party package like NumPy. And it presents a very strong barrier to the optimizer. Unless, so did you take that into account? Or when you see a call to a native function, you're just calling it the Python way and getting back the results?
You are asking if I am optimizing native functions with bootstrapping some-AST. Numba does that, but my JIT compiler doesn't do that. Okay. Thank you.
Okay, we thank the speaker again.